Let's take a look. So let's look at this. This guy. Methyl group. So dimethylamine. Okay. Okay. All right. With a Cl. Okay. It's a salt that's formed, right? From two things. From what? Oh, the Cl would be from HCl. So that's a strong acid. And this other thing's definitely a weak base. So we're expecting an acidic solution. This was also acidic for the same reasons. The NH4, the ammonium ion, came from ammonia, which is a weak base, and the chloride ion came from HCl, which is strong acid. So we had something acidic here as well. We're expecting an acidic solution for this second one as well. Well, what the heck should it look like? This, remember, is a positive ion. So there it is as the positive ion, ignoring the chloride. Add water to it. The water is forced to act as a base. Becomes a conjugate acid over here. This is donating an H+, so it's acting as an acid here, and here's its conjugate base. This is what we want. When we go looking for a number, though, what we find is the K sub B for this. They don't list things that are the ions in the table. So we ended up having to go look for this because it's not ionic. We ended up with a KB listed for this guy. Not what we want. We want to turn it around, right? So we're going to do that same trick, okay? So what I wanted was to have these guys over this, right? I wanted this concentration and this concentration over the concentration of this. What they gave me was for this. So they gave me these two over that. Okay, so I have the CH3, 2, NH2 plus, OH minus, over this guy. Now, if you look at that, you can see this is on the bottom, that's on the top. This is on top, here it is on the bottom. I want this one. If I flip it over, 1 over KB, then these will be correct. They'll be in the order that I wanted, right? So that's fine. That would give me the CH3 and H over the CH3 twice and H2 plus and OH minus. Okay, so now it's at least this way, right? I have these two proper. What am I going to do with that? Well, what I'm going to do is I'm going to say, let me multiply this by KW. Well, what is KW? That's hydronium and hydroxide. This goes away. And now I have exactly what I wanted. So it's a Ka, right? Ooh, my goodness, that's a Ka. And it's going to be the 1.0 times 10 to the negative 14 from the Kw. And then we're going to use the value of the Kb that they gave me. 5.9 times 10 to the negative fourth. And that is going to be equal to 1.69 times 10 to the negative 11. That's what we're going to be using. Okay, this is what we want. This is what we're going to write in our rice table. So for the reaction, we go back to the CH3 to NH2 plus and the water, which we're going to be able to just sort of ignore, in equilibrium. Separate those, and it's going to become the CH3 2NH plus hydronium ion. Okay, there we go. That was R. What's initial? We got to think about that for a minute. Initial. Let's go back all the way up to the top. It's a 0.25 molar solution of this. So if I separate this part off, that's this. Okay. So I'm going to put the 0.25 here. This hasn't happened yet. Great, zeros. Change. If it's a 0, it's got to go up. Each of these, same coefficient, so both are plus x. Where did they come from? This thing falling apart. So our equilibrium, 0.25 minus x, this is going to be x, this is going to be x. When I set it up, I'm going to be x squared over the 0.25 minus x, and that's going to be equal to this guy that we had so much fun figuring out. Does that sound right? Okay, okay, now what? What do we know? Look at how small this is. Wow. This x must be really small. I mean, it's squared, but minus 11? That's crazy. And what did we start with? 0.25? I can safely say that x is much, much smaller than 0.25. Because otherwise I wouldn't get such a small number here. So I'm going to use a shortcut. And that is to say, since x is so much smaller than 0.25, if I subtract it from 0.25, it's not going to make a lick of difference. So I'll say this is just x squared over 0.25 equals 1.69 times 10 to the negative 11. This will avoid having to use the quadratic formula for once. And if I rearrange it a little bit, I'll find out that x squared is 4.24 times 10 to the negative 12. Use my calculator, and I'm going to get 2.06 times 10 to the negative 6 for x. What was x? X was hydronium ion concentration. If I use that, I can do the pH minus the log of this. And I'm going to get a pH of 5.69. The other thing I can notice is that my assumption here is a good one. This only had 2 sig figs. If x is this small, that would be that I would be subtracting 0.0000206. I only had 2 sig figs, so yeah, it doesn't make any difference. So my assumption is a good one, and I can just carry on from there. And this is where I say, you think you've done plenty of work. We have to, though, answer the question. It says I'm supposed to say the difference in pH. Well, here's what I just came up with. And from the previous problem, that was a 4.92. So 5.69 minus 4.92 ends up being 0.77 pH units. Okay, now I need to describe it. This is closer to 7 than the 4.92. So I'm going to say less acidic. Than the NH4Cl.